Electron Microscope. How does electron microscope see the unseen?
What if I told you there is a universe teeming with life, with intricate structures and alien-looking landscapes, all around you, right now? It exists on the head of a pin. It thrives in a single drop of water. It is woven into the very fabric of the clothes you are wearing. This is a realm too small for light itself to illuminate. For millennia, it was invisible, until we devised a new kind of eye. An eye that does not use light, but something much, much smaller. This is the story of the Electron Microscope, our ship for exploring the cosmic ocean of the infinitesimal. Our journey begins with a simple truth. What we can see is limited by the tool we use to see it. Our eyes see only visible light. To go further, we needed a new window. To understand how an electron microscope sees, imagine its light source. Instead of a light bulb, it has an electron gun. Often a heated tungsten filament, working a bit like an old cathode ray tube. It boils off a cloud of negatively charged electrons, then high voltage accelerates and shapes them into a tight beam. All of this happens in a near-perfect vacuum, so electrons fly cleanly without scattering. Powerful electromagnets act as lenses, invisible hands that squeeze and steer the beam, focusing it to below a nanometer across. The electrons are our pen, the magnetic lenses, the artist's hand. When the beam strikes the sample, many interactions occur. Some electrons pass through, some scatter, some knock others free. Detectors catch the echoes, and a computer reconstructs a black and white map of structure. When we talk about microscopes, two words matter: magnification and resolution. Magnification makes things look bigger. You can blow an image up endlessly, but without resolution, it's just a bigger blur. Resolution is clarity, the ability to tell two close points apart. Electrons have wavelengths thousands of times shorter than light, giving electron microscopes far greater resolving power. With light, you see a skin cell. With electrons, the mitochondria, then the folded membranes inside. At the frontier, even large molecular arrangements. So beyond big numbers, a scientist asks, what's the resolution? Can it resolve virus spikes or a hairline crack a few atoms wide? Resolution is the key that unlocks the deepest secrets of the small. Electron microscopes are not all the same. They come in two main flavors, each offering a unique perspective. First, the transmission electron microscope, or TEM. Its key word is transmission. Electrons pass through a thin specimen, sections just tens of nanometers thick, scatter the beam more, forming a shadow-like 2D image of internal structure. TEM reaches the highest resolutions, down to atomic lattices and viral machinery at work. The trade-off is intense, often destructive sample preparation. Second, the scanning electron microscope, or SEM. It scans a focused beam over the surface in a raster pattern, collecting secondary electrons whose intensity depends on angle and texture. The result is a richly textured 3D-looking map of topography. Use SEM for surfaces, wing scales, cratered pollen, even a dust mite's mouthparts. These incredible machines are not curiosities. They are engines of progress that reshaped our world. Imagine fighting an enemy you cannot see. For centuries, viruses were invisible. Electron microscopes changed that. We saw influenza's spherical shells and bacteriophages like lunar landers. Structure guides vaccines and antivirals from day one. In outbreaks, EM gives the first mugshot. In materials science, SMs reveal metals, polymers, ceramics at failure's edge, spotting microcracks before catastrophe. TEM shows nanoscale phases to design stronger alloys. In chipmaking, features are smaller than light can see. SEMs inspect circuits, find defects, and tune processes. From welds to powders, EMs guard quality across industry. Snapshots from an endless album of discovery. From a universe on the tip of a needle to the blueprints of life, EM transformed our place in the cosmos. There is as much wonder below as above. By using electrons instead of light, we opened a new dimension for exploration. TEM looks within. SEM reveals surfaces. They extend our oldest curiosity, turning the gaze inward and downward. Every answer about proteins, metals, and viruses fuels progress. Faced with barriers, we invent new ways to see. Cryo-EM freezes life in its native state, while better detectors and smarter software extract more from every electron. The frontier of the small is as vast as the large. In molecules and cells, countless discoveries remain. So look at your hand and wonder, what else will we find?